So for delta circuit, so we do a paralleling of your resistance of RA here, and so RA to be parallel. So RDC is equal to amount of RA here parallel with the RA here. So RA multiply by 2RA divided by RA plus another 2RA. RA of here plus RA of this angle of part. So you will have 2RA squared divided by 3RA. And so cancel the RA. So RDC will become 2RA divided by 3. And if you rearrange, so you get RA equal to 3 over 2 RDC. So RA equal to 3 over 2 RDC. So instead of you memorize this one, so you better understand in terms of how the formula or how the equation extract from. Okay, hope you understand this one. So again, the purpose of DC test is to determine the RA. So we calculate RA now, just now. RA, how is it related to your RDC? And then a variable DC, when we put the DC source to the two-sided terminal, we shall adjust this DC, and VDC we shall adjust, and at the same time we shall measure the current that flows into your system. Then we are able to know what is your RDC. And so the DC source adjusted to provide maximal stator current and resistance between two satellites, determine the which is determined from the voltmeter and the ammeter reading. We read the voltage and then the I, so we put the in terms of graph. Then we can see, or we can calculate later on the RA, and because RA is equal to the amount of RDC that we have plot or we have calculate, and then divide by 2 for Y connected, and divide by times 3 divide by 2 for delta connected system. And then when we perform open circuit characteristic, means that we are performing open circuit characteristic, and we have let's say our delta connected system open circuit test. And open circuit test, we run the system and at rated speed, then terminal is disconnect from all load. For the first time, maybe we connect the load, and after certain when it reach rated speed, so we disconnect and from the load. Disconnect means that it runs at rated speed, then disconnect. And so by that we shall have almost perfect linear trend in terms of field current. When we increase field current, we set to 0, and terminal disconnect from all load, and field current at the first time we put in, then we set to 0, and we vary and from 0 to maximum, and we measure the terminal voltage here, and we put a voltmeter here, and voltmeter, it's not a source, it's a voltmeter. And when we disconnect the load, we still measure the voltmeter. So what happened to the trend? We measure the EA or the VT when we increase the field current, and disconnect, but we increase field current, so the IA is 0 now. IA is 0, and we increase the this is your field, and we feel IF increase gradually, set to 0, then increase, set to 0, then increase. So we measure the voltage. What are the voltage? So usually the open circuit characteristic will be like this. Instead of we have a linear, but we tend to, after a certain limit, tend to curve. And so B phase now is the amount of EA, because we don't have any kind of element of RA or JXS over here. So this one is neglected, so we consider as your output VA is equal to V phase. So that's for open circuit test. This one is for short circuit test. Short circuit test, that means we perform I field set to 0 again. We set to 0 and short circuit terminal with ammeter. We short circuit this one with ammeter and short circuit. We connect from positive to negative, and at the same time we measure the current. And instead we put a very low resistive load, and we measure the current that flows into your system. We want to acknowledge, or we want to know what is the maximum current that the system can provide. So we set the field current again. IA and IL is measured. IA or IL is measured. The field current is set at 0 to maximum, and IF is varied from 0 to maximum. We measured IA. Just now we measured V out. Now we measured the current that flows into the line. So field set to 0 and increase to maximum. We short circuit the terminals, and so we measure in terms of their current. And so V phase is normal because when we short circuit, so V drop is 0. So EA is equal to the other parameters here, and we rearrange IA to the left, so it becomes EA divided by the total impedance of your system. So we shall see the short circuit characteristic of the system. Then when we combine both graph together in terms of short circuit test and open circuit test, so from short circuit test we set the I short circuit at I rated. We take I rated usually in the nameplate of your system or your motor or generator. You stated the rated current. So that rated current value you plot from the value to the graph of short circuit current and short circuit current. So you get the related field current that usually producing that rated current. So that one you shoot up to the short circuit or open circuit voltage. Open circuit voltage value. So this will become your E open circuit and internal generated voltage of your open circuit system. And from short circuit current get IF using I short circuit at rated here the left. So you get IF not, and so from here you will get your open circuit EOA here, EOC here. And so Z synchronous is equal to EA divided by IA, or EA OC here divided by I short circuit rated. This is I short circuit rated here, IA, and at A here. This is EA at open circuit. So this is the value that you will get, or to represent the parameter of your synchronous machine, synchronous generator. So to get the value of another parameters, you can get from the this is the impedance of your synchronous impedance of the system, and you get your ZS, and from ZS you're able to get your reactance here, and also resistance of the coil. So this is an example that we take from the books. We just add another connection. Instead of just Y, we put delta. So you can practice, and I shall share the solution in the next coming slide.